evening and welcome to Tinkering with Edkelar. Well, it's time for something slightly different, nostalgic this time. It might come as no surprise that I grew up with LEGO Technics. My first ever set happens to be the very first Technics set ever, a yellow forklift, set number 850. Needless to say, as a little kitten, I kept browsing the catalogs and little sneak peeks that LEGO snuck into the instruction manuals. This is where I first saw what looked like a model of a pen plotter, along with some strange controller box. I never found out what exactly that was, but it made a lasting impression. Fast forward to late 2019, when I randomly discovered that combination online. For sale! Well, need I say more? It turns out that this set was part of an educational line and it comes with a neat themed case. Electrically, the set operates with the 4.5 volt system that was state-of-the-art in the 80s. This usually involved 3 C-type batteries in a box, or later a stick arrangement. However, the controller comes with a mains transformer. So far, I only ever saw the 12 volt system with transformers. The motors that came with my set were in a sad shape. I had to order replacements for those, which also were in need of some TLC. A bit of cleaning and a drop of oil makes for a much happier running noise. The controller on its own is not of much use. It needs to interface with a personal computer via a 20-pin ribbon cable. My research showed that there was an 8-bit ISA card for the PC and a user port cartridge for the C64. And since I found software listed for the BBC Micro, I'd think there was one of those too. But these, along with the software, is even more rare than the controller. Pure unobtainium. Reverse engineering it is then. Got to make my own interface somehow. To find out how this thing works, I first need to remove the cover. The case is held shut with 6 plastic plugs. I drilled a hole and used a small screw to pull them out. Corkscrew style. I did trace out most of the circuit and it led to the following big picture. First off, the interface is isolated via optocouplers. The emergency stop button cuts off the resistor array on these channels. This means that hitting the button will turn off all the output channels at once. The 6 output channels can be addressed individually, or 2 of them combined can be used to drive a motor in either direction. The input channels are set up for a detection brick. These bricks contain a small circuit that has a rectifier, an LED and a photodiode of sorts. Together with the encoder disk, these bricks provide pulses as a feedback about number of revolutions. The rest of the board is pretty much just the power supply. The transformer had an awful hum to it. Shame on whoever made this for LEGO for using a completely blank set of screws and forcing me to drill some more holes. And how can that even hum if it is completely potted? Humph! It took some time to pry out that brick and replace it with a new transformer to keep the style intact on the outside. In conclusion, the controller provides 8 bits of data, 6 as outputs and 2 as inputs at TTL level. I decided to use an Arduino as an intermediary. That provides the easiest way for me to connect custom I/O ports to my computer. So, computer to serial port for the Arduino, and the Arduino can then interface with the Lego controller. Time for quite a bit of testing and trials, and baking it into software for the Arduino and the PC. Here's what I came up with. The encoder wheels are rather slow. Anything faster than about 3 changes per second and it will start to miss them. I used interrupts on the inputs of the Arduino to count the ticks, so I don't miss them. On the upside, I determined that the output does support PWM. That means that I can run the motors at arbitrary speeds. The downside here is that the combination of I/O channels I need doesn't give me 6 PWM channels. Darn! So I have to use 3, 1 per motor channel, and reverse the duty cycle when the motor has to run in reverse. Since the motors are anything but precise, I came up with a speed calibration method. The code runs a motor channel with specific parameters and scans the decoder feedback to detect and measure movement at certain speeds. This information is then converted into a translation graph and can be used to make sure a speed between 1 and 100% will result in minimal motor speed up to maximum speed and, hopefully, linearly anything in between. The Arduino software, which I call the driver, translates serial commands into I/O channels and vice versa. There is still a lot of stuff to fix or improve upon. The plan was to have 3 modes in here. An init mode that provides a very raw I/O mode for calibration and project-related setup. Then I have implemented a free mode where the software can pretty much send one command after the other. The third mode would have been a simple automatic mode, i.e. a very simple list of commands that the driver runs through, so there wouldn't be any delay between finishing one command and starting the next one. Like turn motor 3 in reverse, 50% speed, 4.1 seconds and similar. This one is still a to-do. I also created a C# based library for sending commands to the driver. This makes it a bit easier to focus on the high-level stuff while keeping the serial protocol at a lower level for the Arduino. Here the idea was to have a class per operation mode so they can each expose the matching features and it's evident which commands are available at what time. After this heavy coding and bug fixing, I finally can tackle the plotter. Woohoo! The build is fun and reminds me of the good old days of LEGO Technics when there were almost no special parts. Next, I need a program to create a useful drawing. And what better way to demonstrate the technology than my thumbs up icon. Thanks again to Yamavu for providing a nifty stylized artwork. I already have it as an HPGL file for the Iwatsu plotter test. So, writing an HPGL parser. HPGL is a very simplistic format. It consists of 2-letter commands with, depending on the command, some numbers or text as parameters. I wrote some simple parsing code first to get an idea of what I'm up against. Turns out that my little logo was only using 4 commands: in, sp, pd and pu. That is, init, select pen, pen down and pen up respectively. That makes things much easier than I feared. I can ignore the init and pen selection, and then it's only straight lines. No arcs, fills or text to deal with. For converting coordinates to motor commands, I first measured the complete extent between the extreme edges and divided that up by the number of ticks that the encoder wheels made during that distance. Turns out that 1 tick is about half a millimeter, so in theory it would be pretty accurate. If it weren't for an abysmal backlash when changing directions. I tried to come up with compensation code, but the actual backlash is too unpredictable. This is just not a precision device. After a few days of tinkering with a bunch of patch wires, I finally soldered together a perf board shield adapter. I also have a KiCad project for one, but it is really just a 20-pin ribbon cable adapter. I thought I might detect the home position by moving in one direction until the movement stops. But the gearing is so high, the moving parts literally disintegrate before the motor stalls or the belt slips. So I have to manually position the pen in the 0 position before plotting anything. Oh, I did not know that LEGO spacing lines up perfectly with binder holes. And after quite a few trials and fidgeting with the code, I think this is about as good as it will get. Upload the software components to my GitHub account once I added a few more comments to it. And I would love to hear back from people who either have this thing now or experienced it back in school. Please share your experience or memories. that's it for this episode. I hope you enjoyed this more experimental project. See you next time! And stop. No, why is this not working again? It's like oh. Yeah, carry on.